Okay, we're going to continue on with section 3 the chain rule in this video, and we're going to start with this example 13, and this is a doozy to start with. The tangent line of a trig function. Find the equation of the tangent line to the graph of this function, 2 sine x plus cos 2x, at the point pi comma 1, as shown in the figure. Then determine all values of x over the interval from 0 to 2 pi, at which the graph will have a horizontal tangent. So this is a multi-part problem. The first thing that we want us to do is find the equation of a tangent line. So of course we're going to need a point and a slope. You can't write an equation without a point and a slope at least, or 2 points. And here's the function that we're dealing with, and they give us the point. At the point pi comma 1. Pi comma 1 is our point, so we need the slope at that point to write the equation. And again, here's the function. The graph looks like this. We got this little curve action going on here. And then our point is over pi up 1. That's where we want our tangent line to be tangent to the curve, right at this point pi 1. So we need the slope at this point. How do we find the slope at a point? Well, we do that with the derivative. So here's our f of x. We need to find f prime of x. And let's see here, we got no product rule going on, we got no quotient rule going on. Good, so this should be relatively simple. The derivative of 2 sine x is 2 cosine of x, plus, we are going to need the chain rule here, but not too bad a one. The derivative of cosine is negative sine of the same 2x times the inner function's derivative, 2. And here the negative sign will overpower this positive, so we're going to have 2 cos of x minus 2 sine of 2x. Okay, that's our derivative. Again, we plug in an x value, and that will give us the slope occurring at that point. So I guess we're ready to plug in our x value. Our x value of our given point is pi. So we're going to find f prime of pi. F prime of pi. And that's going to be 2 times the cosine of pi minus 2 times the sine of 2x. And remember, we're plugging in pi for x, so this is going to be 2 times pi, or 2 pi. Okay, I hope we remember our unit circle. 2 times the cos of pi. What is the cosine value at pi? Here's our unit circle. Pi would be over here. So we're over here. Cosine is the x-coordinate. The x-coordinate at this point would be -1 minus 2 times the sine of 2 pi. 2 pi is a full circle around, so we're back over here. Sine is our y-coordinate. Right here on the x-coordinate, our y value is 0. So -2 times 0 is 0. That goes away. Our derivative, f prime of pi, equals 2 times -1, or -2. Good point right here is you can stop and say, does that make sense? Is it reasonable? Look over here at the picture. Is this roughly the slope of -2? Well, it's negative for sure. It's going downhill at more than 45 degrees. So yeah, we're probably pretty close, if not exact. So there's our slope. So our slope is -2. Now we can write our equation of the tangent line. And remember, our line is y minus y1 equals m quantity x minus x1. Plug in our relevant information. Y minus 1 equals, our slope was -2. And here we're going to have x minus pi. Distribute the -2. Y minus 1 equals -2x plus 2 pi. And we're not going to get this into perfect slope-intercept form, but we'll add 1 to both sides. Y equals -2x plus 2 pi, and then plus 1. You can think about, y equals mx plus b. Here is our y equals m. Our slope is -2x plus, this is our b. It's just a little weird looking. It's not just a number. It's 2 pi plus 1. Okay, so that's the first part. We found the equation of the tangent line at the given point. Next, determine all values of x on the interval where the graph has a horizontal tangent. Well, what does it mean to have a horizontal tangent? It means that the slope is 0. The derivative is 0. And we can get an idea from the picture here how many of those there might be. Here we have a hill. At the top of the hill, there'll be a flat spot with the slope of 0. And then we're down into this valley. At the bottom of the valley, there'll be another horizontal tangent line. And then up here on this peak hill, we're going to have another horizontal tangent line. And then down at the bottom of this big valley, we'll have another horizontal tangent line. And then here, 2 pi is where we end. If we went farther, there'd be another one up top here, but they only want the ones between 0 and 2 pi. So as we work through this, we're going to have to keep in mind that there should be 4 of these spots with a horizontal tangent line. And how do we find horizontal tangent lines? Remember, the slope is equal to 0. So we set our slope, f prime, or our derivative, f prime of x, equal to 0. And I did erase that, but our derivative was 2 cosine of x minus 2 sine of 2x, and we set that equal to 0. So let's see here. We're going to have to dig deep back into some pre-calc to get this to work out nice. We did do problems like this in pre-calc, but it's been a nice long summer, so I'm sure we've forgotten a few things. What I'm focusing in on right here, this sine of 2x. We have a cos of x, and this is a sine of something completely different. There is a trig identity that we can use to expand that, so to speak. So our 2 cos of x will stay the same for now, and then we're going to have minus 2 inside these brackets, the sine of 2x. We can replace that with something else, and that something else is 2 sine x cos x. That trig identity is probably somewhere in the back cover or the front cover of your calculus book somewhere. So the sine of 2x we replaced with this. That's equal to 0. Let's see here. We can divide everything through by a 2. Divide this term by a 2. That 2 will cancel. Divide this term by a 2. It'll wipe out this 2 here. 0 divided by 2 is still 0. So here we're going to have the cos of x minus, this 2 did not cancel. We'd still have to distribute this, and that's just going to go in with this sine of x cos x. 2 sine x cos x equal to 0. And let's see here. I guess we can factor out a cosine. So we'll pull a cos out front, cos of x. Here we factored a cosine out of here. We factored this cos out, so there's a 1 left in its place. Minus, we factored out this cosine, so we're just left with 2 sine x. And that's equal to 0. Okay, so we took our derivative, set it equal to 0, and how do we solve that is we factor the left side, and now we're going to set each factor equal to 0. And here's our 2 factors. Let me move these up to the top. So the first one, cos x. Here's our 2 factors, cos x, and then this other one we'll set to 0 next. Where does the cosine of x equal 0? Remember, back to the unit circle. We have this point is 1, 0. This is 0, 1. This is 0, negative 1 down here, and negative 1, 0. Where is our cosine value, or our x value, equal to 0? Well, that happens at pi over 2 radians, and then down here beneath it, between the 3rd and 4th quadrants, at 3/2 pi. So we have our x equal half pi, and x equal 3/2 pi. Second factor, 1 minus 2 sine x. 1 minus 2 sine x equals 0. Subtract 1 from both sides. Negative 2 sine x equals negative 1. Divide both sides by negative 2. Sine x is now a positive half. Where on the unit circle does sine equal positive a half? Remember, sine is our y-coordinate, so it's going to be somewhere up here and somewhere up here. And that just happens to be 1/6 radians, 1/6 pi radians. And over here in the second quadrant, 5/6 pi radians, 5 pi over 6. So those are the x values on the interval in which the graph has a horizontal tangent line. That was a tricky one. A lot going on in that example. Okay, now on to the derivative of the natural log function, just the ln, and this is pretty much a piece of cake. Here we have the ln of x, the natural log of x. Its derivative, when we take the derivative with respect to x, is just 1 over x. It's like this x here that we're taking the natural log of, just drop down to the denominator, we put a 1 over top of it. What happens if it's not as simple as ln of 1x to the first? What if it's a composite function like ln of x squared or ln of x to the 5th power? Well, that's just going to be d dx of the ln of u. Remember, u is our inner or of the composite function. Well, that derivative is, we just take this u and move it down to the denominator. U is our denominator. The numerator above it is the derivative of u. So whatever you put down here, take its derivative, u prime, and put it in the numerator spot. Here in the theorem box, d dx, the derivative with respect to x of the natural log of u, is 1 over u times the derivative du dx, which is the same as u prime over u, as long as u is positive. U has to be greater than 0 because we cannot take the log of negative numbers. So let's check a few of these out. Again, these shouldn't be too bad. The derivative with respect to x of the ln of 2x. Well, again, our answer is going to be a quotient. The denominator is just the 2x. That 2x dropped right down here. And the numerator is the derivative of u. Well, our u here is 2x. Our numerator then is its derivative 2. And then we can cancel here. So that'll simplify down to 1 over x. Here in letter B, it's a little more complicated. Now it's the natural log of a quantity, x squared plus 1. Well, our answer is a quotient. The denominator is that x squared plus 1. The numerator is that derivative. What's the derivative of x squared plus 1? 2x. And there we go. Letter C, they do kick it up a notch, so to speak. Now we have a product rule. X times the natural log of x. Well, the derivative of x is 1. The derivative of ln of x is 1 over x. So now we do a product rule. The first, x, times the derivative of the second, 1 over x, plus the second, ln of x, times the derivative of the first, 1. And here, what is x times 1 over x? Well, that would be x over x, or 1, plus the ln of x. And the last one here, we're going to now make that ln a quantity raised to a power, so a little chain rule will be happening here. Move this up. The ln of x quantity to the 3rd power. Well, by the power rule, bring that 3 down. 3 times the ln of x quantity, now to 1 power lower, 2, times the derivative of the inner function. The inner function is ln of x. That derivative is 1 over x. And I guess if you wanted to combine the 3 and the 1 over x, you could have 3 over x times the ln of x quantity squared. Now don't forget, we had properties of logarithms, logarithmic properties. And we learned those in pre-calc, and those can take what could be a very complicated derivative and make it much, much easier. Here we have the ln of this x plus 1 square rooted, or you could make that to the 1/2 power. And if we wanted to take the derivative, we could move that square root of x plus 1 to the denominator, apply the chain rule, get the numerator, and look for ways to simplify it. But if we remember our properties of logs, we can get to a much simplified answer very quickly. This is the ln of x plus 1 quantity to the 1/2. Now in pre-calc I said over and over, this was my favorite of all the properties of logs. I hope you remember what it is. F prime of x. Remember, with this exponent, we can bring it down front of the log. So we can make this 1/2 the ln of now just the simple quantity, x plus 1. And now we can take that derivative. Oh, that prime shouldn't be there. Excuse me. That's not our derivative yet. We just applied a property of our logarithms. Now we're ready to take the derivative, f prime of x. So constant multiple, 1/2 is just going to stay there. What is the derivative of the ln of this quantity? Well, that's just a quotient. The denominator is the quantity, the numerator is its derivative. And then we could, I guess, write it like this, 1 over 2 times the quantity x plus 1. And there's our derivative. Okay, Okay, example 15, some more log properties aiding to differentiation. And if we look at this original function, this is a mess. The natural log of, we have this quantity in the numerator, divided by this quantity in the denominator. If we wanted to just do it as a straight up differentiation of a log, we would take this whole thing, that would move down and become our denominator, and then the numerator would be that derivative. And if we wanted to derive just this, look at this mess. We have the quotient rule, a numerator and denominator. And when we take the derivative of the high function, where we would have to apply the product rule here, and part of that product rule would require the chain rule. And when we derive the denominator, that would be a quantity to the 1/3 power, we would also have to use the chain rule there. So that would turn into a big mess really fast. And if we did everything right, we'd get the right derivative. It might not simplify down and look exactly like what we'll find when we go through this example, but it would be correct, and it'd be a lot of work, and every step is another chance to make a silly mistake. But if we remember our log properties, we can make this a little easier. The first one, we have the log of a quotient. What if I had the ln of x divided by y? If we remember our pre-calc last year, that is the ln of the numerator minus the ln of the denominator. So we'll apply that here first. F of x, and this is not the derivative yet, the ln of a quotient is the natural log of the numerator, and that was x times x squared plus 1 quantity squared, minus the ln of the denominator. And I'll rewrite that as a rational exponent, 2x to the third minus 1 quantity to the half power. So using this property of logs, we broke our quotient up into a difference, a subtraction. Now in the first term, we have x times this quantity squared. And if we think back to pre-calc, what if we had the ln of x times y? Well, that breaks down into the ln of the first thing plus the ln of the second thing. And this is still our f of x, not the derivative yet. The ln of x times this other quantity is the ln of the first thing, x, plus the ln of that quantity, x squared plus 1 quantity squared. And then we have our minus the natural log of this quantity to the half power. And now I hope you already saw it, my favorite log property. We can move these exponents down in front of the natural logs. This is still f of x. We haven't derived yet, but we're setting it up to make it real easy. So this is going to be plus 2 ln of x squared plus 1 minus 1/2 the ln of 2x to the third minus 1. All right, and now it looks like we're ready to take the derivative. We've done a lot of work to get ready to, and you're going to see that this is going to really pay off and make this derivative easier to handle. F prime of x. Well, the first term, ln of x, easy derivative, 1 over x. Plus, we're going to have 2 times the derivative of this. And the ln of this quantity, its derivative is, our denominator is that quantity, x squared plus 1. And our numerator is the derivative of that denominator, 2x. Minus 1/2. Here again, we have a ln of a quantity, so that same quantity is our denominator. The numerator is its derivative. What would that be? 6x squared. And it looks like there's going to be some stuff that'll cancel, and we can combine maybe, make it look a little prettier. Okay, first term's going to stay the same, 1 over x, plus, here 2 times 2x is 4x over x squared plus 1. And what can we cancel here? It looks like on this diagonal we can factor out a 2. That'll factor out to a 1. This will become a 3. So we have minus 3x squared over the quantity 2x to the third minus 1. Now I see it year after year, students are going to want to, oh, I can cancel those x squareds out. No, remember this is a quantity in the denominator. It's 2 terms, 2x to the third minus 1. If you want to factor out any variable, it has to occur everywhere. Here it occurs in the numerator, it occurs in this term of the denominator, but there's not an x to factor out here with the 1 at all. So that's as simple as we can make this derivative. And moving on. Theorem 314. absolute value. Remember, natural logs, we can only take the log of positive numbers. The graph looks roughly like this. Natural log. We cannot put negative x values in it. So if you have the ln of the absolute value of u, it's still just u prime over u. Like if we did the ln of the absolute value of sine of x. Remember, sine can go between +1 and -1. We don't want to take the ln of those negative numbers between 0 and -1. And if we took the derivative here, d dx, the denominator would be sine x, and the numerator would be its derivative. Derivative of sine is cos of x. Now, what about bases other than the exponential? Exponentials with other bases like a to the x power. The base of a natural log exponential function is e. This natural base can be used to assign meaning to the general base a. So this isn't anything to do with calculus yet. This is just the definition of an exponential function of base e. If a is a positive real number not equal to 1, and x, the exponent, is any real number, then the exponential function to base a, denoted a to the x, is defined this way. A to the x is e raised to the ln of a times x power. If a is 1, then y equals 1 to the x is equal to 1, just a constant function. Log functions to bases other than e can be defined in much the same way as exponential functions to other bases are defined. So if a is a positive real number not equal to 1, x is also a positive real number, then the log function of base a, denoted log base a of x, is defined by this. 1 over the ln of a times the ln of x. Well, remember, when we did these in pre-calc, log base a to the x, we could rewrite that as the ln of x over the ln of a. This went up in the numerator, the natural log of x. This subscript here, the base number, went down to the denominator also with its own ln. Excuse me, that should be the ln of a there, not x. That's an a. ln of x over the ln of a. And that's just reminding us, redefining what these are in terms of the others, that we did see that in pre-calc. So what are the derivatives? To differentiate exponential and log functions to other bases, you have two options. Use the definitions of a to the x and log base a of x, and differentiate using the rules of natural exponential and log functions, or two, use the following differentiation rules for bases other than e. So if you have something, d dx of a to the x power, that derivative is ln of a times a to the x. Second one, what if this is a composite function? If it's a to the u, well, it's going to be the exact same answer, ln of a times a to the x, but we're going to tack on a times du dx, or u prime, if you prefer that notation. Just that inner function's derivative gets multiplied on the end. Now for the non-natural logs here we have log base a of x. We want to take the derivative of that, and its derivative is just 1 over the ln of a times x. Whatever this number is a, goes right here after the natural log. Whatever this number is x, just moves right over here. 1 over natural log of a times x. And again, number 4 here is if it's sort of a composite function, anything more complicated than just x to the first. If we have an inner function u, it turns into 1 over the ln of a times u, whatever that inner function is, times u prime, the derivative, du dx. So let's take a couple of these for a test drive here. Letter A, y equals 2 to the x. Well, our derivative, y prime, equals, the 2 to the x is going to stay exactly the same, 2 to the x. And what we put in front of it is the ln of the base 2. And we could write it like that. The ln of 2 times 2 to the x power. Letter B, it's sort of the same, but now we do have a sort of composite function. Now our exponent is 3x instead of just 1x. So our derivative, y prime, is going to be, part of it is the original function, 2 to the 3x. In front of that, we put the ln of the base, so that's going to be the ln of 2. And then we tack on the end via the chain rule. The derivative of 3x is 3. And to make it look a little prettier, I'm going to put my constant first, 3 times the ln of 2 times the original function 2 to the 3x. Okay, and one more to go. This is the last example for 3.4, the section on the chain rule. There's a lot going on in here. So now it's log base 10 of the cosine of x. Well, if we follow the template from the previous page, the previous slide, what's going to go down here in the denominator? This is log base 10, so we're going to have the natural log of 10. And then up in the top, we'll have our, just by the formula, there's a 1 up there. And then we multiply that ln of 10 by whatever we're taking the log of. Here it is cos of x. And this is our inner function. This is sort of our u, so we got to multiply by u prime. What's the derivative of cos of x? Negative sine of x. And let's see if we can simplify that at all. We can move that negative sine x up top. So we'll have negative sine x over the ln of 10 times the cos of x. And it's not bad if you leave it right there. We can go a little bit farther. This ln of 10, that's just a number you can punch in on your calculator and get a decimal for. And since it's in the denominator, we can drag it out and make that the denominator of its own function, 1 over the ln of 10. And then we're going to have times negative sine over cosine. Well, that negative can come out front with the 1 over ln of 10. And then what is another way to write sine over cosine? Well, that's tangent, the tangent of x. Negative 1 over the ln of 10 times tan of x.